Hello, my name is Drake Dibby. This is my EGR 150-100 Section B EggDrop project. So this is a table of contents. This is for if anybody wants to come in here and wants to look at something in particular but doesn't want to look at the whole thing, they can jump to the corresponding slide. This is a quick executive summary of the whole project. It has some data in here and the principles we used to actually design the structure, the final design, and the initial design. We'll just talk about it briefly, and then how we could actually change the structure. So I'll leave it here for a brief second if you want to pause and read it. Okay, moving on. So the project description. So we're going to design a structure to catch a free-falling egg from 6 feet without cracking or breaking the egg, and we want to achieve this repeatedly. So the only materials we were allowed to use were black plastic drinking straws and masking tape, nothing else. And you couldn't change the properties of the straw, so you couldn't cut it or do anything like that. You needed to leave it in its general straw form. And the key concepts we use, we'll talk about it in the future, but elastic deformation and plastic deformation. So these are properties of materials when you apply stress and energy to them, and these are key components to designing the structure. The energy calculations, we'll talk about that later as well, but the potential energy calculated was 1.08 joules. And the impact force, the actual weight that is being applied upon impact, we got 54 newtons if we're assuming that we have 2 centimeters of deformation, which is what I actually designed these structures to accommodate, was 2 centimeters. So these are the planning dates. This is what worked for me. It may not work for everybody else, but this is how I decided to plan everything out and achieve a nice and stress-free project. This is a Gantt chart. It's a good way to visualize the actual dates and timelines. We don't have a lot of overlap in the beginning, research, initial design, calculation. It's all sort of the same thing and can be done at the same time. Construction didn't really overlap with much. I feel like when I'm making something, I need a little more time just to focus on that. And then drop testing obviously had to wait until after construction because you can't drop the egg if there's nothing to drop it into. And then right here in the home stretch, I had a lot of overlap, which really helped me finish up the whole project. And so now we're going to talk about deformation. When I initially learned deformation, I learned with a lot of charts and graphs, and they were kind of confusing. But I found this figure online that I thought was a great representation of elastic and plastic deformation. So elastic deformation is going to be when we have a material and we apply stress to it, it's going to change shape. And that's what's going on here, right? So we have material, they're pulling it each way, it's going to change shape, but when we remove that stress, it's going to return back to its initial state. That's elastic deformation, right? The temporary change in material. And then we have plastic deformation. So that's when we're going to take the same material and we're going to apply stress to the point where it surpasses elastic deformation. So it's not going to be able to return back to its original state. We're going to permanently damage this material. And when you relieve the stressors, it's going to be deformed. It's going to look like this. So plastic deformation is to be a permanent shape change in material when a force exceeds its elastic limit. So it's absorbing the energy. It's not entirely breaking, but it's going to change the shape forever. These are the calculations that I did initially before I even designed the project because I needed to know what I was actually trying to accomplish. So I calculated the potential energy with a 60-gram egg, 9.28 meters per second squared, that's just a constant of gravity, and a height of 6 feet, 1.82 meters. And so that resulted in 1.08 joules. We round to 3 significant digits. And then the impact force calculation. This is interesting. So this is how much weight and force it's actually going to take to save the egg, right? And so I used that energy joules, this energy divided by deformation distance or whatever you want to call it. And so I had 2 centimeters, but we only use meters in these formulas. So I got 54 newtons. That's actually an incredible amount of force that this egg is going to be putting on the structure, and I took that into consideration when I made the designs. And you'll see on the initial design, I kind of overbuilt it in regards to that 54 newtons. So this is going to be the initial design and analysis of the first structure. And as you can see from this little isometric view, I made trapezoids here to give strength, but let the straws deform and bow a little bit. And I left these skinny because I wanted this structure to shift and move and twist. Right? I wanted the straws to deform in a way elastically that would absorb energy and then come back. Now, the downfall of this design is this basket's very small and it's very rigid. And so that's where we actually had problems down the road. So we'll start with the materials used. I had 17 straws. So this is like a pretty conservative amount of material, right? I think 150 straws was the limit. I used 17 to build this, but I did use a lot of tape, 224 millimeters. I feel like that's a lot. And you can see here, there's a lot of tape wrapped up, which actually led to part of the problem of it being too rigid. So we'll see here. I'll mute this and then we'll watch it. So I'll start scrubbing. So you can see it actually caught the egg. And at first I thought this was going to be a success and wow, this project's easy, I'm done. But what happened was after repeated drops, the constant stress on the egg actually caused damage to the same egg. Now, the project didn't state if we were using different egg every drop or what. So I just used the same egg and it started cracking because of the force applied here. And I thought of that as a failure. I wanted it to catch the same egg repeatedly without any compiling stress. But if we see here, it actually does do what I had intended. So we'll jump back. We'll scrub through. As you see this egg fall, everything's going to bend. Everything's bending like we talked about before. Now when it hits the basket, I left about 2 centimeters. It might be a little more, 2.5, 3 over here. It's pretty hard to bend these straws. But as it deforms, this actually strikes the ground. And I think that's where this repeated stress is. You know, these straws are in V's. They're very rigid. When they strike the ground, I think it's sending the force into the egg. And it catches it. And the trapezoids shift the way I designed. I mean, I wanted it to shake kind of like a skyscraper would twist upon a earthquake. But this is another flaw. Look at that egg. There's nothing retaining that egg. It's just bouncing. And I didn't like that. I didn't want that to happen. That didn't feel safe to me. You know, that's not repeatable. We're not trying to build a trampoline. We're trying to create a structure to catch the egg. So, to me, this is a failure. And we'll come back to this. So the final design. I used less tape, a couple more straws. So I kept in mind with that, like way under budget. I want to use way less material, but I want to achieve this thing. I want it to be repeatable. And you can see in the isometric view over here, this is one straw. So this is as rigid as this is going to be. None of these straws have been deformed. Like, it's just 2 straws. And now, this is where I use my plastic deformation. I actually shaped these legs and these arms for the basket overnight. I kept them bent, taped them up, and I wanted them to deform and keep this angle on them. And thoughts that they would use plastic deformation or elastic deformation after the fact to spread out and sprawl, which it does. But this is where I feel like the design really strives, is this removable basket, as we'll call it. So I enjoy watching auto racing, and a big thing in auto racing is stopping or transferring the energy that the drivers have when they impact walls. So this is actually designed after a safer barrier, where we have strong structure, strong structure, strong structure, as where things aren't going to push through it. But what they can do is it'll dissipate energy by elasticity. So it's going to hit each side and it's going to bow. And you'll see in the video it bows when the egg hits it. And it creates just enough friction, kind of like a catcher's glove, to hold the egg. And this piece goes on top. But you couldn't really see the whole thing, so I separated it. I used plastic deformation here to actually create this little pocket so the egg could fall right into it. And we'll see in the slow-mo. And so we'll rewind. So I counted these as success. I had 10 plus drops. Caught it every time. As you can see, the egg falls. Okay. The egg falls. And it lands right into the basket. And if we cut back a couple frames, as you can see, so this right here, this is deforming elastically. So this is going to go back to its shape, but it's absorbing this. This is that 2 centimeters that I'm talking about right here. This is going to move. It's going to pick these legs up off the ground. And these legs are going to spread force. But what they're going to do is they're going to push it back up. So the egg falls into the basket. It has enough friction on each side. As you can see, the egg is fully secure. The egg's not going anywhere. It's jumping around. It's in the basket. The basket's holding onto the side of it. I had multiple drops of this, and I would consider it a success. And my big goal was to have 2 centimeters deformation, keep that constant 54 newtons, and make sure that the egg is going to be retained. So when the egg comes in here, it might bounce around, but it's just going to hit these walls, and these are going to deform slightly. I mean, not very much. They're going to deform slightly, and it's going to hold the egg snugly enough that it's not going to come back out. Now you see I have some pre-tensioned pieces like this, so it's going to fall. And as you see, the basket slides up the arms. This is the intention of the arms being as tall as they are. Is as this deforms down 1 centimeter so far, maybe 2 centimeters, the basket goes up. But as you see how these are bent out, these are the same. These two where I use plastic deformation to permanently change their shape, they're bent out. They're keeping force on this, making sure it doesn't slip out. This is cupping the egg. This is catching it. And now it's fully secured. So I would consider that a success. I think we had repeatable, successful catches. It's flexible and lightweight. We use much less material. So in theory, engineering, the cost would be significantly lower than a much larger design. And then we optimized elastic deformation. I feel like what we wanted to implement was elastic deformation, and we did that. I mean, you can see here that it actually catches and returns back to where it's going to be. And this is a repeatable design. So the only downfall here is probably that it bounces around. We could probably add some more weight, but as a final design of what we're going for, you know, this is a proposal to get a bid or a job. I think this gets it done, right? We can show that we can do it for much less, and if they have other requirements, we can implement that later. But I think this is a clear success. So the conclusion, we safely caught the egg both times. I would say the first time it wasn't as reliable. We had some extraneous stress on the egg after repeated drops, and that's why I came up with this second design. And we had over 10 successful drops with the final design. The initial design, you know, damaged the egg slightly, but the final design is repeatable. And I think we balanced the elastic and plastic deformation. You know, we use plastic deformation in our design to make sure that the legs stay in a certain shape to implement elastic deformation. We absorbed all the energy, The egg didn't bounce out, stayed captured, and we achieved that 2 centimeters of deformation, which was intended. So we could probably optimize some crumple zones, especially in the initial design, if that's where we end up going with. That basket was far too rigid. In the second design, we could add weight to their structure, reducing all that bouncing. The bouncing could be a problem if the project had said catch the egg while maintaining the same place, like within a 1 meter circle. Then that's probably something I would attack for another rendition, because it did bounce around a little bit, and with the landing structure you kind of wanted to stay stable. So these are the references. This is actually the link to that cool little figure explaining elastic deformation. And then this is where I got the information based off of like what elastic and plastic deformation is, and then some of the formulas, and also some information about the eggs, because that was very important. Thank you for listening to my project, and I hope you enjoy it, and I hope you think I implemented it successfully.